Welcome back everybody to my channel. In this video we want to solve problem 256 paint houses. In this problem we are given a row of n houses and the objective is to paint all of these houses with either red, green or blue, and the condition is that no two neighbor houses can have the same color. So for example, if I paint some house with green, I can no longer choose green for these neighbor two houses, and I can only choose red or blue for both of them, and likewise for red and blue as well. So the only condition is no two neighbor houses can have the same color. For the input of this problem, we are given a 2D array of size n by 3 that each row specify the cost for each house, and each column specify the cost for different colors. So for house 1, I have 3 values. For house 2, I have another 3 values. And the first one specifies the cost of painting the house 1 with red, painting house 1 with green, and painting house 1 with blue, and etc. So the objective of this problem is to minimize the total cost of painting all of these n houses that satisfies the condition that I explained earlier. That was no two houses can have the same color. So one way of solving this problem is to run a backtrack recursive function starting from house 1, similar to the problem that I explained in some other video of putting n queens in a n by n chess table such that no two queens are threatening each other. So we can start with painting the first house with red, and then for the next one we have two options. So we call the recursive function of painting this house 2 with green and blue, and then for red we return the minimum of these two values plus the cost of painting the red. Similarly, run it for green, run it for blue, and then at the end just return the minimum of these 3 recursive backtrack functions that we call on the first house. Similarly, you can also consider this problem as a graph problem of n times 3 nodes. So we can say we have some nodes, and then we know that since no two neighbor houses can have the same color, node red of house 1 is not connected to node red in house 2, but it is connected to green and it is connected to blue. So likewise, green is not connected to its green node in the next house, but it is connected to red and blue, and etc. So we can consider this problem as a BFS. We can run a shortest path BFS problem starting from 3 nodes. So we should run BFS 3 times, and the objective is to reach the last row, house n, in either of these houses, and then return the minimum total cost. So in both backtrack recursive or this BFS, we are jumping into some states and we have to calculate some similar states over and over again. But instead, we can go with a DP approach to minimize the total cost of not computing some similar states over and over again. So let's say we already know the total costs of painting n-1 houses, and we have a new house that we want to add to our table. We know that this is the total cost of painting house 1, painting house 2 up to n-1, and we want to add this new house. So in order to compute this last state of the total cost that end up the very last house has color red, is the cost of this painting this new house with red, and added by the minimum of these two values. So we know that if we ended up painting the last house with red, we can not consider this state that the previous house, the neighbor house, has color red. So the minimum of these two values. Similarly, for green, it is the cost of painting this new house with green added by the minimum of the total cost already computed in the previous states, house n-1 painted by red or blue. So for that, first of all, let's consider the edge cases. What happens if we have only one house? If we have only one house, we don't have any neighbors. So since the condition is to paint all of these houses, let's keep track of the state, the current state, as the costs 0. So if we don't have any, not more than 2 houses, if we have only one house, so this is the 1 by 3, so it's a array of size 3, and then at the end we should just return the minimum of the current state. In order to make our solution, our dynamic programming approach, memory efficient as well, do we need to keep track of all n-1 houses? So the answer is no, because at the end, what is matter as a solution of this problem is to return the minimum of cost of ended up painting the very last house, either red, green, or blue. So the minimum of these 3 values is important as the answer of this problem. So it doesn't matter what are the total cost of painting 1 house, 2 house, up to n-1 houses. So we don't have to keep track of all of them. So with a constant extra memory of size 3, we can update it. So whenever we add a new house, we have our current state. So the current state as we have specified here. And then whenever we have a new house, we recalculate our current state by adding the cost of this new node plus the minimum of these 2 values, then painting this new house with green, with the minimum of having the total cost of the previous house painted in red and blue, and etc. So for each house in costs 1 onward, for the next one, we should recalculate the current state. And the current state has always 3 values. So we should compute the R, G, and B. So we can say for each color in range 3, since we have 3 colors, the current state would be the house price of the color. So we have 3 colors. The cost of painting the current house with that paint, with that color, plus what are the previous states. So for each color, we should compute the minimum of 2 other values. If we are going with red, then we should find the minimum of the green and blue from the current state, which is specified the n-1 houses. And similarly, if the index of this C is blue, then we should only consider red and green of the previous states. So for that, I want to define another function, a helper function, that returns the adjacent node or the connected nodes that we specified earlier in our graph connection. So for each index or for each color, so if it is 0, we should return a list of 1 and 2. If it is 1, we should return if it is 1, we should return 0 and 2, and lastly, if it is 2, we can only return 0 and 1. So the connected nodes. So simply, we can return, since we have only 3 states, we can only consider C plus 1, the modular by 3, and C minus 1 modular 3. So if C is 0, then C plus 1 modular 3, the remainder by 3 would be equal to 1. And then C minus 1 would be, since C is 0, would be minus 1. And then if we compute that, it would be equal to 2. So with that, we don't have to define, manually define or write a dictionary or something for computing what it is connected to. So what is matter here, the current state of the other color, the other color for let's say for each index for I in the adjacent of C. So for each given, we are iterating through 3 colors from 0, 1, and 2, and this function returns 2 neighbor connected cells. So for red, it returns green and blue. For green, it returns red and blue, and for blue, it returns red and green. And we are computing the minimum of those 2 values plus the cost of painting the current house with this color. And then we iterate through them in ON. So we are visiting each house 1 time. So the time complexity of our solution is ON. And the space complexity of this solution is constant, since we are only allocating an extra memory of size 1 by 3 for this problem. So the total time complexity would be ON, and space complexity would be O1. And it should be enough for solving this problem. Yes, and let me submit that. There we go. So faster than 77%. We use dynamic programming to solve this problem by constant extra memory for this solution. So that was everything for this problem. Hope you enjoyed this video.